All right, so for this question, they're asking us about any relative extrema and intervals of increase or decrease. So this part of the question, the first half you could say, is a review. So how do we figure out relative extrema? We figure out relative extrema by working with f prime. And this is the part that I'm going to kind of fast forward through because this was done in the previous lesson. The new part that I want to focus on is figuring out inflection points and intervals of concave up or concave down. And the way that we get all that information about concavity is by working with f double prime. So the process is the same for f prime and f double prime. The process is identical, but the meaning of everything is different. Okay, so let's go through the 3 steps again to figure out relative extrema. Step 1, derive. We derived here using the quotient rule. Step 2, or actually part of step 1, set the derivative equal to 0. Here's the cleaned up derivative. Because there's a numerator and a denominator, I set both the numerator and denominator equal to 0, and I tried to solve each equation. From the numerator, I got 2 solutions, negative and positive root 2. And from the denominator, because I had to square root a negative number, I ended up getting no solutions. So anytime I have a solution from anywhere, numerator or denominator, for f prime, those are called critical numbers or critical points, and the reason they are critical, the reason they are important, is because they could be relative extrema. So step 1, figure out your critical numbers or critical points. Step 2, make a sign chart to figure out if indeed they are relative extrema, or just to get more information about it. So I put negative root 2 and positive root 2 on my sign chart, and over here I put values of 0. If they had come from the denominator, what would these values have been? D and E. Okay, but because they came from the numerator, the values of f prime are 0 and 0. And then I took numbers in each interval, here, here, and here, plugged it into the derivative, and checked to see if I got a positive or negative result. The thing about this derivative, the way it's set up, is that the denominator, because it's quantity squared, will always be positive. So all I really have to check for is the numerator. So what I did was I plugged in 3 different numbers. I plugged in negative 2, and I got negative divided by positive, which is negative. I plugged in 0 into f prime, and I got positive over positive, which is positive, and then I plugged in positive 2, and I got negative over positive, which is negative. Okay, so now I know, because I have a sign change, that this is a relative extrema, more specifically, a relative minimum. And because there's a sign change here, this is also a relative extrema, more specifically, a relative maximum. And now I know all my intervals of increase and decrease. This here, from negative infinity up to negative root 2, is an interval of decrease. The one between the negative root 2 and positive root 2 is an interval of increase. And then here, I have a decreasing interval from positive root 2 up to infinity. So step 1, find the critical points. Step 2, make a sign chart to get more information about relative extrema and increasing and decreasing intervals. All right, step 3 is to translate your sign chart into interval or inequality notation. So I've just rewritten my intervals of decrease in interval notation, interval of increase, and I've specified the x-coordinates, at least, of my 2 extrema. And I kind of want to show you what you did here on the graphing calculator. So what you did is you were able to figure out the relative min. You claimed that the relative min was at negative root 2, and indeed it was. It's right there at negative 1.41, which is negative root 2. And then you're also able to figure out the only relative max, which you claimed to be at root 2. And if I calculate root 2, I also now have the y-coordinate of my relative max, which is right there. Okay, and this is your original function, x divided by x squared plus 2, that rational function. All right, furthermore, you can see your interval of decrease. Here's the decrease. And then here's your short period of increase, and then your final interval of decrease. Okay, so to answer any concavity or inflection point question, we need to take f prime and derive it. So I took f prime, I used the quotient rule, and that's how I got f double prime. So let me just walk you through that real quick. So this is low, denominator, times d high, derivative of the high, the numerator, which is negative 2x, minus high times d low, derivative of that denominator is right here, all over low quantity squared, we go happily. So there's my f double prime. Okay, same process, I repeat the same process. I'm going to take my f double prime and I'm going to set it equal to 0. Okay, but before I actually, and then I'm going to try to solve this equation, but before I can do that, I really need to clean this numerator up a little bit. So I got two options. I can either choose to FOIL that and distribute that and kind of multiply everything out and then try to combine like terms. That's one way to simplify the numerator. Or I can choose to factor out 2x and an x squared plus 2, which is what I'm going to decide to do now. So if I factor this out of here, I'm still left with a single x squared plus 2. And if I take this out of here, I'm still left with 2 and a 2 minus x squared. All right, and then I'm going to go ahead and distribute this 2, and I'm going to combine like terms in here. And I'm going to end up with the part I factored out, plus the simplified part in here, which ends up being 6 minus 1x squared. And my denominator is actually now to the 4th power. And I'm still working on simplifying my f double prime before I try to solve anything. So here's a cancellation here. And I think now I have a very manageable and simplified second derivative. So this is the second derivative, or this version of the second derivative that I want to be working with. So because it's a fraction, I need to set the numerator equal to 0. And I need to set the denominator equal to 0. And then I need to solve both equations. When I go to solve the top equation, negative 2x equals 0, that gives me one solution of x equals 0. And when I go to solve this quadratic, 6 minus x squared equals 0, it gives me two solutions. X equals plus or minus root 6. So again, like I said, it's the same process with different meaning. These are also called critical numbers and critical points, but these are critical points on f prime as opposed to critical points on f. From the bottom, from the denominator, I get, once again, no solutions because I can't square root a negative number. So, like I said, the process is the same. Step 1 is to get the derivative, in this case f double prime, and set it equal to 0 and get your critical numbers or critical points. Now, the meaning is different. Why are these critical points or critical numbers on f double prime? It's because they are possible inflection points. But I don't know until I go through step 2, which is to make a sign chart. Okay, step 2, we need to make a f double prime sign chart using the most simplified version of f double prime. So I found 3 critical numbers by working with f double prime. I put them here in my sign chart, negative root 6, 0, and positive root 6. And now I'm going to pick a number less than negative root 6, like say negative 3. I'm going to plug it in here to f double prime. I get positive times negative, which is negative. Negative divided by positive is negative. Okay, now I'm going to pick a number between negative root 6 and 0, such as negative 1. And I'm going to plug it in here. Everywhere I see an x, and I end up getting a positive sign. I'm going to plug in a number between these two in green, like say positive 1, and I'm going to plug it in here, f double prime, and I get negative times positive, which is negative. Negative divided by positive is negative. And finally, I'm going to pick a number bigger than root 6, like say 3. I'm going to plug it in here. Negative times negative is positive. Positive divided by positive is positive. So, step 2, make a sign chart. The sign chart is going to give you all the information you need. If you see a change in sign, that particular x is considered an inflection point. So, was there a change in sign here? Yes, negative, positive. Is there a change in sign here at x equals 0 for my green part of my sign chart? Yes, so that's an inflection point. Is there a change of sign here at root 6? Yes, so that's an inflection point. So step 2 is to make the sign chart and then determine whether your critical numbers are actually inflection points by looking for a change in sign in your f double prime row for your sign chart. Once you know the location of, or at least the x-coordinates of your inflection points, you then know all intervals. You can now describe the concavity of the function f. Like for example, if f double prime is negative, you know that f is concave down. And if f double prime is positive, you know that f is concave up. And so on and so forth. So really, this sign chart gives you all the information that you need. Step 3 is then to take the sign chart, like you did with f prime, and translate it to interval notation using f double prime. So just a quick little review. This is what we did for f prime. See, we put everything in interval notation, and now we're going to repeat the same process with f double prime. So, for example, we're going to say that from negative infinity, up to this number, negative root 6, and from 0 up to this number, positive root 6, we have intervals where our function f is concave down. And then in this interval right here, from negative root 6 up to 0, and from positive root 6 up to infinity, are intervals where my function f is concave up. I want you guys to realize that f prime gives you information about f. It describes f for you. And f double prime also describes f for you. Okay, so they're used to give you more information about f than you would have had with algebra. And then finally, last but not least, at x equals negative root 6 and at x equals positive root 6, we have an inflection point, or inflection points. And also, at x equals 0, we have our third inflection point. So I just listed out all the inflection points. And keep in mind that all this information about concavity and inflection points here in this orange box, all that information came from working with f double prime. And all the information about relative extrema, or increasing and decreasing intervals, all that information came from working with f prime. So the process is identical. You work with f prime the same way you would work with f double prime. It's just the information you get from f prime is different from the information you get from f double prime. And everything is used to describe the original function that we were talking about, f, the rational function that we were talking about, f. All right, so I have inputted the original function, the rational function, x divided by x squared plus 2. And this is the function you've analyzed. And with algebra, you could have figured out this x-intercept and some more information. But with calculus, you can figure out a lot more. Like, for example, you figured out that there's a relative min here at negative root 2. There's a relative max here at positive root 2. You also figured out that there was an interval of decrease, interval of increase, and an interval of decrease. So that's all the information you figured out with f prime. What you figured out with f double prime is that there are 3 inflection points. And let me show you exactly where they are. So there's one inflection point when x is negative root 6. So I'm going to have the calculator figure out what the y coordinate is. So when x is negative root 6, you can see that y is negative 0.3, which is right there. And right there you have an inflection point. So what you have is you have your curve going from concave down, see that, to concave up. So the concavity changed right there, so that's why that's an inflection point. At x equals 0, you have another inflection point, because you change from concave up, which is this little bowl right here, to concave down. And then at positive root 6, which is here at 2.45, right around here, you have another inflection point because you went from concave down, see that, to concave up. So f double prime gives you a whole other set of information about the function f, which is what we graphed here.